Hey, Math 30-2s, how's it going? We're going to start our new chapter of exponential functions. So this week's going to be a pretty easy one. The first two lessons are not too bad. The third lesson, a little bit trickier. Then next week, we'll finish off this chapter with modeling, more regressions, just more equations, more graphing to do. That's pretty much how it's going to end up for the rest of the year, too, because the next chapter after that is all about logarithm functions. They're just kind of the opposites of these ones. Which can be the same idea, which we just introduce what they are, do some math, and then some regressions and modeling. And then they'll end off week 11, and then week 12 here, we might have a kind of more interesting week regarding puzzles and stuff that they're just fun to do, and they're part of the curriculum. So yeah, we'll see how that turns out. Let's talk about an exponential function. So an exponential function, very different graphs, very different kind of functions than polynomials and sinusoidal functions that we've done. Sinusoidal functions go up and down forever, and they go off in both directions forever. Polynomials, they have very distinctive shapes, and these ones have very distinctive shapes. Sometimes you get a little bit confused with cubic functions or quadratic functions just because of how it starts going upwards, or depending on which way you're looking at my graph thing here, it's going upwards or it's going downwards. But you're going to see how they work out. The key thing about an exponential function is where is the variable, the x variable. Okay, so remember in polynomials, my x variable is the base, and then it's raised to a number. Right? In sinusoidal functions, it's inside that sine equation, right? So it's a sine x or cos x or whatever. But this kind of, when we're talking about exponential functions, the exponent is where the variable is, right? So this is very important to know where the x is. So if you ever see the x in the exponent, then we have what we call an exponential function, right? So they're pretty easily identified, right? As soon as you see the x in the exponent, we have these nice little exponential functions. And there's some restrictions to these, which is to watch out. If there's a number in front, like this is what we call the coefficients, kind of like the leading coefficients from polynomials, right? If there's a number in front, that number just can't be zero. If it was zero, then you just have a flat line. It wouldn't be exponential anymore. It'd just be a constant zero. So it'd just be a nice little flat line. Other things here is that the b value has to be greater than zero, which means it has to be a positive number. We're never going to deal with the ones that have negative numbers. No other courses really do either. We run into a problem when we have negative numbers. When you try to take the square root of negatives, you're not allowed to do that. Okay, so b's always have to be positive, and you'll notice that all the b's are positive here. And also b's cannot be 1, and the reason they can't be 1, because as soon as that becomes a 1 here, if that was a 1 raised to the power of anything is just 1. So it doesn't really change. So again, it becomes a constant function because of that. So you just want to make sure that a is not 0 because we don't want a constant function. And then b can't be 1 because we don't want a constant function. We want this very distinctive shape of graph. So to find out what that distinctive shape of graph is and how these actually differ from other ones, is we're going to just do a few calculations here. I'm going to start off with the middle. I'm going to work my way backwards and forwards here. Okay, so let's start off in the middle here where this says x equal to 0. So I'm going to take 10 and I'm going to raise it to the power of 0. Okay, so what that means is I'm going to multiply 1 by 10 0 times. Right? Because you don't see what's in front. Like up here, you can also write that. If you don't see the number in front there, that little invisible 1, you just assume there be a 1 there. So this is technically what it is. It's 1 times 10 to the x. So like here you can see there's a 2 in the front, right? So what this is saying, when you see a 0 there, you're going to see 1. Oh, sorry, just 1 second. Okay, you're going to see a 1 times 10 0 times. Okay, so that's just 1. Yeah, it's just 1. Anything raised to the power of 0 is also 1. That's one of the rules of exponents. You'll see that later on couple lessons from now, when we review the rules of exponents, if you raise it to the power of 0, you have, just have a 1. Okay, so that's going to start off at 1. So that's pretty key. So x is equal to 0, y is equal to 1. So that's, I don't know how this scale works. It's 100. That's way down here. Way down here, pretty small. But you can see the scales go by 200, 400, 500. Like that's 100, that's 50. So it's like an itty bitty. So it's like really, really far down there. Okay, so we have 1 point so far. So that's our y-intercept, right? So I'm just going to write that in there. Y-intercept. Since x is equal to 0. Remember how to find the y-intercept is when you make x equal to 0. So if I put x equal to 0, I always get my y-intercept. Okay, so the next line just says, okay, 10 to the power of 1. Okay, so that just says I'm going to take 1 and times it by 10 once. Okay, so I get 10 on that one. The next one down says 1 times 10 squared, which means it's going to be 1 times 10 twice, which is 100. And then the last one here is going to be 1 times 10 3 times. And you can see what's happening here. No, actually, I'll just write my last one down before I talk about what's happening. And then we'll just look at the pattern. Okay, so it starts off at 1, 10, 100, and 1,000. So what's happening on the y side? So first of all, I'm going to mention what's happening over here. So this is my y-intercept. Okay. What's happening as I go from one side to another? So as long as the x side is nice and constant, so this is just plus 1, plus 1, plus 1. As long as that's nice and constant, what happens on the other side is you times it by what we call a common ratio each time. So this is times 10, times 10, times 10 as you work your way down. Okay, so if we follow that logic, and you can see that I'm going backwards here in this next one, so I'm going to go backwards from the middle. So minus 1, minus 1, minus 1. So I can assume that if I go backwards, rather than going forwards, so forwards is times 10, I'm going to divide by 10. So this is 10 is my common ratio. It's the number that I'm multiplying this by each time, okay? So if I multiply it to go forwards, I'm going to divide to go backwards. So that's what a negative exponent actually means. You're going to divide, or you're going to take the reciprocal. So rather than multiplying by 10 each time, a negative exponent would mean I'm taking the 1 and I'm dividing it by 10 each time. So this is going to be 1/10. So as a decimal, it's 0.01. And then if I go back again, let's just double check. So I'm going to go 1 times 10 to the negative 2, which is 1 divided by 10. And then if you want to, you can hit another divide by 10 in there, or you can put both those 10s on the bottom. So this would be 1/100th, which is 0.01. And if I divide by 10, again, you notice the decimal place is just moving once each time. So this would be 1 divided by 1,000, which is 1.001. Okay? So I'm dividing by 10 each time as I go here. So hopefully that pattern holds true for the next one as well. So the 10 is just because of this number here. So this here is my common ratio. Okay, so let's see how this graphs out. So at 1, I'm at 10. Okay, so that's 150. 10 is right about there. It's way higher. It's 10 times higher than the first number, but they're really, really small, so it's hard to see where that would be. So I'm just going to make my dot a little bit bigger there. These next ones are not too bad. So like at 2, I'm at 100. So I'm right here. Okay, so I can actually plot that. And then I'm at 3, I'm at 1,000. So you can see there's quite a jump. We call that an exponential jump, where it seems like it's starting off small, and then all the numbers just start getting bigger and bigger. If I wanted to go even more, 4 would be at 10,000. It'd be 10 times this. It'd be 10 times higher up there. If I go backwards here, I'm just going to have really, really small numbers. Now the key is I'm going to keep on dividing by 10. And all that's going to do is just move this decimal place one space over each time. But it'll never, ever get to 0, because the only way to get to 0 is the numerator has to be 0. I'm just dividing by a bigger and bigger number, and you can just punch it in your calculator. Go 1 divided by 10, and then hit answer divided by 10, hit enter a bunch of times. Just keep on going. You're just going to keep on adding zeros to it, but it'll never be 0. It'll get really, really close, but never be 0. So that's going to be key. It'll never be 0. So this line here is going to be skimming right across the x-axis there, and then it's going to skyrocket up on that side there. Okay, so let's answer a few questions about this graph first, and then we'll go to the next side over here. So how many x-intercepts are there? Well, there are none. This graph can never cross the x-axis. Y can never be 0. Y can never be 0. It can get really, really, really big, or it can get really, really, really small, but it'll never equal 0, just based on the logic that you're always dividing by 10, but you're never subtracting by 10 or something. So when you divide by numbers, it just gets smaller. So there's none. My y-intercept, okay, that's a pretty easy one. X was 0, 1. You could just write 1 if you wanted to. It doesn't matter to me. My end behaviors, remember there's end behavior. Where does it start? Where does it end? Actually, which hand am I doing? Okay, where does it start? Where does it end? All right. So it starts in quadrant 2. Remember, this is quadrant 2. This is, oops, sorry, this is 2. This is quadrant 1. Got it right in there. That's quadrant 1. Down here is quadrant 3. And quadrant 4. You notice that the graph is never down there. So it's going from quadrant 1 to quadrant 2. I always like to go from left to right. My domain, XER. Now, the reason behind this is that I can put whatever exponent I want here. These are just nice numbers here, but I can have 1.5. I can have an exponent of a half. That's 0.5, sorry. I can have exponent of 1/3. I can have exponent of 6.3 or something, right? Or negative 2.45. Or irrational numbers. I can have like to the power of square root of 2 or the power of pi if I wanted to. So I can have those kind of exponents. And there's no limitations to those kind of exponents. So my domain is going to be XER. I can put whatever number I want there. My domain is going, or so my range is going to be, because it can't be 0, because I remember I get really close to 0, but it can't be 0. My y values have to be greater than 0, but they're not equal to 0. All right, so there's no line underneath that equal sign there. All right, because I can't have an x-intercept. So it's never equal to 0. It gets really, really close. It has to be greater than 0, but not quite there. Okay, so let's look at this next graph and see how that one looks. Okay, let me just double click over here. We're at a pretty big video so far. Let's just do this one more graph and just double check. And then we have a few more graphs down here. Yeah, and then we'll make this a two-parter here. Okay. So the first one's going to be, we'll start with the logic. We'll start right in the middle at the y-intercept. This is my y-intercept again, because x is equal to 0. So I'm going to have 2 times 5 to the power of 0, which is 2 times 5 is 0 times. So it just ends up being 2. Okay, which makes it, okay, so we had a 1 in the front before. We ended up with a 1 as my y-intercept. We had a 2 in the front. We ended up with a 2 as the y-intercept. Okay, the next one's just saying 2 times 5 one time. Okay, 2 times 5 is 10. Okay, the next one is saying 2 times 5 twice. So 2 times 5 times 5, which is 2 times 25, which is going to be 50. The next one's going to be 2 times 5 times 5 times 5, so 3 times. Now you see the pattern here is I'm adding an extra 5 each time. Like here, I'm adding an extra 10 each time. So this is going to end up being 250. So it's just going to be times 5 times 5 times 5. So we have a common ratio of 5. Cool. Okay, so the common ratio is 5. I'm multiplying by 5 each time. So that probably means that just if I go backwards, I'm going to divide by 5 each time. So 2 to the power of 5 to the negative 1, which would be 2 divided by 5. punch in your calculator. Let me just get my calculator out. 2 divided by 5. So we have 0.4. Okay, so that ends up being 0.4. The next one here is going to be 2 divided by 25, or 5 times 5 on the denominator there. So I'm just divide by 5. And all I did on my calculator, I don't know if you can see that, is I just took the answer, the previous answer, just divided by 5. So you can see that I'm using my phone as a calculator here. It's kind of fun. You can download those apps onto Android. And this one here would just be 2 to the power of -3, which is going to be 2 divided by 5 times 5 times 5, all on the bottom. So I'm just going to take this answer I have my calculator, divide by another 5. But you notice it's not quite 0. And if I just keep on hitting enter, right, keep on dividing by 5, divide by 5, I'll just keep on adding zeros, right? But I'll never quite get there. I'll never get to 0. It's just going to get smaller and smaller and smaller. So no matter how many times I divide by, I'll never get 0. So let's see what that graph looks like when I graph it here. 20, 10, 2 would be right about here somewhere. That's right about 2. That's my y-intercept of 2. If I go over 1, I should have 10. If I go over to 2, I should have 50. So every single little boxes are 10 here. And if I go to 3, I go to 250. So right about there. So it's not as steep as the previous one, because I'm only multiplying by 5 each time, not multiplying by 10 each time. So it's not going to be as steep, but still pretty steep. The next dot would be 5 times higher, wherever that would be. And then if I go back here, it's hard to draw these dots in here, but you know, I'm just going to draw these dots just above the x-axis, not touching the x-axis, but just above it. There you go. Cool. Now, what do they have in common? What do these two graphs have in common? Well, the two graphs never cross the x-axis, so we have no intercepts here. They have the same end behaviors. I'm going to talk about the y-intercepts in a bit here. They have the same domain, and they have the same range. So they have a lot in common. And really the only difference between these two graphs is the y-intercept. Well, this y-intercept is just 2, and the other one was 1. Okay? So I'm going to stop this video here, and we're going to talk about 2 different types of graphs where we have fractions inside the brackets there rather than whole numbers like 10 and 5. Okay, I'll see you in the next video.